In this video, we're going to take a look at concavity and then how to tell if different parts of the graph are concave up or concave down. So if the graph of f lies above all of its tangents on an interval I, then it is called concave upward. If the graph of f lies below all of its tangents on an interval I, then it is called concave downward on an interval. So let's consider this function here. I've marked off points A, B, and C, where A is less than B is less than C. And if we take a look, we can say that if f double prime of x is greater than 0 for all x in the interval, then the graph of f is concave up on the interval. So think of concave up as holding water. So if you want to take a look, this would be from this point A to this point B on the graph. So we see that A is less than x is less than B. So when x is between A and B, it's concave up. Also from C onward to the right, it is also concave up because it would hold water. Now, if f double prime of x is less than 0 for all of the x values in the interval, then now we say that the graph of f is concave down on the interval. So this time, think of concave down as it's spilling water. So this would be from the left all the way until A. So all our x values are less than A. Or we can also say it from B all the way to C. Now these points that I've marked off, A, B, and C, they're special because this is where the concavity changes. So we can see that it's concave down and then up, and then down and then up. So these points are called inflection points. So what do these conditions mean geometrically? So let's consider this curve below here. So we can see that we have three tangent lines. We start off with tangent line A, and it has a negative slope. And then we get tangent line B with a zero slope. And then we have tangent line C having a positive slope. So as we move from left to right, we can see that the slope of the tangent line increases. But the slope of the tangent line is given by the first derivative. So to say that something increases means that its derivative is positive. So if the first derivative is increasing, then we need to take a look at the second derivative, which then must be positive. Since the first derivative is increasing, then the second derivative is positive. So this means that the curve is going to be concave up. Now let's consider this other curve. So this time we have a tangent line A starting off to be positive, then B is 0, and then we have tangent line C, which is now negative. So this time, as we move from left to right, we can see that the slope of the tangent line decreases. So the slope of the tangent line is given by the first derivative. Okay, and to say that something decreases means that its derivative is negative. So to say that the first derivative is decreasing, meaning that it's negative, then we need to take a look at the second derivative. So this time, f double prime of x must be negative. And when this happens, we have something that is concave down. So the two pictures exemplify the geometric meanings of concave up and concave down. So now we're going to go on to how to find concavity, or where it's concave up and down, algebraically. So to do this, we first set up a sign chart, but this time instead of for the first derivative, like we did for increase and decrease, we're now going to set up a sign chart for the second derivative using the critical points. Now, similar to the first derivative, the critical points will occur when f double prime of x equals 0, or when f double prime of x is undefined. So these are called breakpoints, in which the graph could possibly change concavity. On each interval, we need to then determine, which is determined by the critical points. We're going to pick a point at random, and then we're going to plug it into f double prime. Excuse me. Now, if the point gives a positive value for f double prime, then we know that f double prime is positive on the interval, and then the function is going to be concave up. Okay, so if it's positive, it's going to be concave up. And then we're going to put a little plus sign above the interval, and we tend to draw a little U because it's kind of like holding water, like a cup, below it. Similar to when we drew the downward sloping arrow, or the upward sloping arrow when we're doing increase and decrease. Now, likewise, if a point gives a negative value, this time for the second derivative, then you know that the second derivative is negative on the interval, and then now the function is concave down. So we then put a little minus sign above the interval, and then we draw an upside down U, or an upside down cup, spilling the water out. So let's take a look at the graph that's pictured here. So determine the intervals on which the function is concave up, and the intervals on which it is concave down. Find the x-coordinates of any inflection points. So from A to B, we can see that the graph is concave up, and then also from B to C, and then also from D to E here. All right, so it is concave up when x is less than A. Oh, sorry, what am I saying? From A to B, and then also from B to C, and then finally from D to E. Okay, then we can see this one point is concave down from C to D. All right, so we can see that from A to B and B to C, it's all concave up. So B is not an inflection point. However, at C and at D, it changes concavity. So these 2 points are inflection points. So inflection points at x equal to C and D. All right, let's do one algebraically. So we first find our first derivative, which is 4x cubed. And then now we need to find the second derivative. So it's going to be 12x squared. Set this equal to 0 to find our critical points. So here x is equal to 0. So draw my sign chart, place 0. I'm going to put f double prime of x here to remind myself that I need to find numbers and then plug it into f double prime. All right, so I'm going to pick -1, and then I'll pick 1. So I'm going to put -1 into my second derivative. When I square, I see it's going to be positive. When I put 1 and I square it, we see that's going to be positive as well. So both of these will be positive. So I'm going to draw a plus sign on the top to say it's positive, and then I'm also going to draw a little U underneath just to remind myself that these 2 parts are holding water, and then we have little U's. So we can now say that the graph is concave up when x is less than 0 and x is greater than 0. Now, unlike increasing and decreasing, where we always used equal to symbols in the inequalities, concavity does not use an equals. We don't put a line underneath. This also has no inflection points. Because there's no change in concavity. All right, let's do one more. So here, we're going to find our first derivative. So when I bring down the 4, I get x cubed plus 3 over 2 x squared minus 6x. Find my second derivative, I get 3x squared plus 3x minus 6. Set this equal to 0. I'm going to factor out a 3 as well. And I can factor this. So I get x plus 2 and x minus 1. So here x is equal to negative 2 and positive 1. So draw my sign chart, negative 2 and 1. And I'm going to put double prime to remind myself when I'm plugging in. So I'm going to use negative 3, 0, and then 2. And I'm going to plug it into my second derivative, which is this one here. So when I plug it in, I find that this is going to be positive. So I'm going to draw a U. This middle part is negative. Draw an upside down U. And then the last piece is positive. So then I draw a U again. So my graph will be concave up when x is less than negative 2 and when x is greater than 1. So that's at these points here. Actually, now that I have so much written, let's highlight that. So that would be this point and this point. And it's concave down from negative 2 to 1. Now, because it changes concavity at negative 2 and 1, negative 2 and 1 are called my inflection points. So inflection points occur at x equal to negative 2 and 1.